Okay, folks, in this next video, we're going to get into this idea, this concept of activity, which is used quite often when we're dealing with non-ideal solution behavior. So the first type of activity we're going to talk about is the solvent activity. And here in this discussion, I'm going to use capital A to denote the solvent, okay? So there's a couple ways we can think about this. The most common is to think of it as the ratio of the observed vapor pressure over its pure vapor pressure. So for example, this PA right here, that would be the observed vapor pressure of a solution, okay, of a solution. Whereas PA star would be the pure vapor pressure of A just by itself. So now here, as we can imagine, the activity becomes this limiting relationship as we move in and out of ideal and ideal dilute conditions. So for example, as the mole fraction of A approaches 1, so as our solution becomes more dilute, the activity of that solution will approach that of its mole fraction. Another way that we can write the activity in a more general way is by noting that the activity of a substance equals its gamma value here, which is the activity coefficient, okay, times the mole fraction. And once again, this is a limiting relationship. So as the mole fraction approaches 1, the activity coefficient will approach that of 1. So we could also rewrite the chemical potential expression, right? Where mu A, this is our chemical potential of the solution. Mu A star is that of the pure liquid. And now, instead of taking natural log of the ratio of the vapor pressures, it's the natural log of the activity. So here's a little graph that came out of my PhD thesis as a demonstration of the activities of an NaCl aqueous solution. So first, I'll point out the red line here. That's Raoult's law. And you notice that there's some curvature there because this was calculated in terms of weight percent instead of mole fraction, so that's why there's some curvature. And then the black line are the empirically determined activities of an NaCl solution based on the observed vapor pressure as a function of weight percent. And so what I'll point out here is at an NaCl weight percent of 0, that would correspond to a chi solvent of 1, right? When the weight percent of the solute is 0, it's a pure liquid. And so what you can see right here is the activity is approaching that of 1, but it is also approaching identical values as Raoult's law. So it's entering that ideal dilute regime. The other thing I'll point out here is at this here 75% activity, or 0.75 expressed as a decimal, that corresponds to a saturated solution of NaCl. And the reason why that's important and why it was important for this work is if we want to calculate something really fundamental like the vapor pressure of the ocean, which is predominantly a saturated NaCl solution, right? Well, Raoult's law would predict this, but measured values actually suggest that it's down there. And so if we used like 90% of the vapor pressure of water as the vapor pressure of the ocean, that would be disastrous in climate models. So we would get a lot of stuff wrong by using the ideal value as opposed to the measured activity value. So we can also talk about activities in terms of the solute. And this is very similar here. So I'll say B is my solute molecule, where PB is now still the observed vapor pressure of the solution. But now KB here, that is my Henry's law solubility coefficient, like what we discussed previously. So we can write the same thing, that the activity coefficient is or the activity is the activity coefficient times the mole fraction. But now where this is different in the solute activity is that the activity of the solute will approach that of the mole fraction as the mole fraction approaches 0, right? So it's the opposite of the solute, okay? And then similarly, as the mole fraction approaches 0, so as our solution becomes more and more dilute, the activity coefficient approaches that ideal value of 1. So we can also write solute activities in terms of their molalities or even their molarities. So that's oftentimes more convenient than mole fraction. And now you can see here we replace mole fraction with this ratio of terms. So that little b of B, that is the molality of the solute. And now that B naught, that's our standard molality, which is 1 mole per kilogram. So it's divided by that standard value to make the units work out, right? So we could also write the activity in terms of the molarity, which would be, right, use the brackets, right? We hopefully remember brackets mean molarity. And then divided by standard molarity, which is just going to be 1 mole per liter, okay? So that B naught and C naught are used as a convenience to make the units work out. So then the last activity to discuss is the ionic activity. And with this kind of notion, right, that the more concentrated our solution becomes, the less ideal it is. But now we have to consider the effect that the charges of our solutes have in the case of it being an ionic solution. So here those red, the small ones, are cations, and the blue are anions. And that sphere kind of represents like a snapshot in time of the solution. And what's important to note here is depending on the charge of our cation and anion, we might see a very different snapshot, right? We might see very different amounts of anions surrounding cations or vice versa. So the first thing we need to consider is the ionic strength, which goes as the following. So that is the ratio of our molalities, right? And now we're using this subscript I to denote that this is summed up for both the cation and the anion. And this Zi squared, that is our charge. And so again, we sum this up for cation, and then we, or for both the cations and the anions. So I'll draw your attention immediately over to this chart right here, ionic strength. And these are the generically calculated values. But what I want to point out is when you have a 1-to-1, a positive 1 and negative 1 cation to anion, the ionic strength is identical to its concentration, whether expressed in molality or molarity. But now, as we get to higher charges, the ionic strength becomes significantly different than the concentration. So for example, if you have a 2-to-2, the ionic strength is now 4 times the concentration, which means the ideality is going to be 4 times as worse, 4 times more into the non-ideal regime. So now that we've talked about ionic strength, we have to consider the activity coefficient, gamma, right? And notice the A and B here. This means that this is an empirical law. So there are fit coefficients that go with A and B. And there you can see the ionic strength is given in this equation right there. So now if we calculate what the activity coefficients are based on the molalities and the charges, you'll notice here for this very dilute concentration, 0.001 molal, the activity of our 1-to-1, right, positive 1 potassium, negative 1 chloride, it's nearly that of 1, the ideal value. But if we look at a 2-to-1 ionic compound, the activity has deviated more significantly from 1. And as we get into more and more concentrated solutions, you can see our activity coefficients become less and less ideal. And I'll point out that in this chart right here, this 0.725, that's a mistake. The value should continue to decrease as the concentration increases. So in other words, as we get a more and more concentrated solution, the activity coefficient deviates from that value of 1, indicating that it's a less ideal solution. Okay, we'll see more of this activity business in equilibrium. Activity is used ad nauseum in the discussion of chemical equilibrium. Okay, I'll see you in the next video.